In an era when the boundaries between credible journalism, speculative science, and outright misinformation have become increasingly blurred, skepticism is no longer optional. It is essential. The modern media ecosystem places rigorously vetted scientific research side by side with viral social media claims, AI-generated fabrications, and half-understood interpretations of complex studies. This environment makes it dangerously easy for bold but poorly supported ideas to gain traction, especially when they promise answers to humanity's biggest questions. Few claims are as sweeping or as tempting as those that purport to explain the nature of the entire universe. It is precisely for this reason that extraordinary caution is required when evaluating proposals that challenge foundational principles of cosmology. A recent example that has captured widespread attention is a paper suggesting that our universe may exist inside a gigantic black hole. The idea is undeniably dramatic and immediately sparks the imagination, evoking images of nested realities and cosmic recursion. The study, authored by Lior Shamir, a computer scientist at Kansas State University, was published in March in the monthly notices of the Royal Astronomical Society, a journal known for its long history and high academic standards. Publication in such a venue naturally lends the work an air of legitimacy, encouraging both the public and some scientists to take notice. However, the prestige of a journal does not exempt any individual paper from scrutiny, replication, or critical evaluation, especially when the conclusions are so far-reaching. Shamir's analysis draws on observational data from the James Webb Space Telescope, the most powerful space observatory ever built and a cornerstone of modern astronomy. Using a large sample of distant galaxies, he examined their apparent rotational directions and reported a surprising asymmetry. Roughly two-thirds of the galaxies appeared to rotate clockwise relative to the Milky Way, while only one-third rotated in the opposite direction. At first glance, this imbalance seems to contradict one of the most deeply ingrained assumptions in cosmology, the cosmological principle, which states that, on sufficiently large scales, the universe is homogeneous and isotropic, meaning it should look essentially the same in all directions. Under this principle, there should be no preferred direction of rotation, and galaxy spins should be evenly distributed between clockwise and counterclockwise orientations. The apparent violation of this expectation is what makes Shamir's result intriguing. If the imbalance is real and not an artifact of data processing, observational bias, or statistical fluke, it would suggest that the universe has a built-in directionality. Shamir interprets this as possible evidence that the universe itself may be rotating. From there, he explores several mechanisms that could give rise to such cosmic rotation, ultimately emphasizing one particularly provocative hypothesis, that our universe exists inside a massive black hole. Because rotating black holes are a natural consequence of general relativity, a universe born inside one might inherit angular momentum, which could then cascade down through cosmic scales, subtly influencing the rotational properties of galaxies billions of years later. The implications of such a conclusion would be staggering. A rotating universe would require modifications to standard cosmological models, and the idea that our cosmos is the interior of a black hole would fundamentally alter our understanding of space, time, and cosmic origins. Some proponents argue that such models could potentially address unresolved puzzles like dark energy, the observed acceleration of cosmic expansion, or the persistent discrepancy known as the Hubble tension, where different methods of measuring the universe's expansion rate yield conflicting results. Beyond academic implications, these ideas have undeniable cultural appeal. They're the kind of concepts that inspire documentaries, philosophical debates, and late-night conversations about reality itself. Yet excitement must not be confused with evidence. Astronomers and physicists have explored both rotating universes and black hole cosmologies for decades, even centuries, and their existence in the scientific literature does not imply they are correct descriptions of reality. In 1949, the mathematician Kurt Gödel, famous for his incompleteness theorems and a close associate of Albert Einstein, found an exact solution to Einstein's equations that described a rotating universe. Gödel's model was mathematically consistent, but physically strange. allowing for closed time-like curves that made time travel to the past theoretically possible. Gödel himself used this result to highlight conceptual weaknesses in general relativity, not to argue that we actually inhabit such a universe. Subsequent observations, particularly of the cosmic microwave background, have placed extremely tight constraints on any large-scale cosmic rotation, making Gödel-like universes highly unlikely. Similarly, the notion that our universe might reside inside a black hole has long fascinated physicists. Once black holes were recognized as genuine astrophysical objects rather than mathematical curiosities, it was natural to wonder whether the Big Bang could be interpreted as the formation of a black hole in some higher dimensional or parent universe. At a superficial level, the parallels are enticing. Black holes contain singularities, points where density becomes infinite and known physical laws break down. When cosmologists extrapolate the universe's expansion backward in time, they encounter a Big Bang singularity with similar mathematical features. Black holes are bounded by event horizons beyond which information cannot escape, while our universe has a cosmological horizon that limits what we can observe due to the finite age of the universe and the speed of light. These similarities invite speculation, but resemblance alone is not proof. Crucially, the differences between black hole interiors and our universe are profound. The Big Bang singularity is not a point in space. It is a moment in time. Every location in the universe shares the same origin in the Big Bang, whereas a black hole's singularity exists at a specific place within spacetime. Inside a black hole, all paths lead inexorably toward the singularity, with space and time effectively swapping roles. In contrast, our universe is expanding, with galaxies moving away from one another as space itself stretches. These behaviors are fundamentally incompatible within the framework of known physics. Any model that attempts to reconcile them must introduce new assumptions or speculative extensions to general relativity, none of which have yet been supported by empirical evidence. This brings the discussion back to Shamir's galaxy rotation result. Before invoking exotic explanations, scientists must exhaust more mundane possibilities. Observational astronomy is riddled with subtle biases. The apparent rotation of a galaxy depends on image orientation, classification algorithms, redshift effects, and the limitations of telescopes and data pipelines. Even a small systematic bias in how images are processed or interpreted could produce an apparent asymmetry when none exists. Independent analyses using different datasets, methods, and teams are essential to determine whether the effect is real. Historically, many claimed anomalies have vanished under closer scrutiny or with improved data. Moreover, even if a genuine asymmetry were confirmed, it would not automatically imply a rotating universe or a black hole origin. Local cosmic structures, selection effects and surveys, or unaccounted for astrophysical processes could influence galaxy spin distributions without violating the cosmological principle on the largest scales. Science advances not by leaping to the most dramatic conclusion, but by carefully ruling out simpler explanations first. The public reception of such ideas highlights a broader challenge facing modern science communication. In a media environment optimized for attention rather than accuracy, speculative interpretations often travel faster than cautious caveats. Chatbots can confidently hallucinate details. Headlines can exaggerate tentative findings, and nuanced discussions can be flattened into click-friendly sound bites. As a result, preliminary or controversial research can be mistaken for established fact long before the scientific community has reached any consensus. None of this means that bold ideas should be dismissed outright. Speculation has always played a role in theoretical physics, pushing researchers to explore the boundaries of existing frameworks. However, speculation must be clearly distinguished from evidence-based conclusions. At present, the idea that we live inside a gigantic black hole remains firmly in the realm of hypothesis, not demonstrated reality. It is an intriguing thought experiment, a useful prompt for examining the limits of cosmological models, but not a claim supported by robust observational proof. In the end, the true lesson of such debates may be less about the structure of the universe and more about how science works. Progress is slow, iterative, and often unglamorous. Extraordinary claims demand extraordinary evidence, and until that evidence appears, skepticism is not cynicism. It is responsibility. In a time when misinformation spreads as easily as wonder, learning to tell the difference is perhaps the most important cosmic skill of all.